Gnan, and I'm working at the CNR in Rome. And this work has been done in collaboration with Emanuela Zaccarelli and Francesco Sciortino from CNR and the Department of Physics, La Sapienza. So what I'm going to show in this last talk of today is how percolation allows us, a solvent that is close to percolation allows us to control colloidal behavior, and also how quenched and annealed disorder in the colloidal solution can give different results on colloidal interactions. Why do we care about this? It's because one of the biggest challenges in soft matter is to develop new phases by controlling colloidal particles for the generation of new materials. So then the question is, how can we do that? So there are two strategies mainly. One is to build colloidal building blocks that self-assemble into targeted structure. So here there is a number of these particles that can be synthesized. But the drawback of this strategy is that these particles are hard to synthesize, so you cannot make many of them. So a second strategy that one can use, and the one that I will talk about, is to induce effective interactions among colloidal particles. What does it mean? It means to add in solution with colloids some macromolecular additives, which can be polymers or microgel or smaller molecules, that mediate the interaction between among colloids and give rise to unexpected interactions between colloidal particles. The drawback of this strategy, of course, there is always a drawback, is that sometimes it's difficult to derive analytically, but there are still some cases in which it's possible to derive, to have a theoretical approach. For instance, the most known example is the depletion attraction. So you have colloids in solution with polymers that can be considered as ideal, and these hard sphere colloids feel an attraction because of the presence of polymers in solution. And for this, it's possible to derive an analytic expression for the effective interaction. But we can go beyond, actually. So sorry, I forgot to say that from a theoretical point of view, what we have to do when we calculate the effective interaction is that we rewrite the Hamiltonian of the whole system. So we have the term associated to the colloids and the one associated to the additives and the cross term of the cross interaction. And we rewrite the Hamiltonian in order to have a total potential that is given by the direct interaction between the colloid plus an additional term that mediates the interaction between the colloids, in which all the degrees of freedom of the additives in solution are integrated out. So this term depends only on the position of colloids on their distance. So the step forward, the standard depletion effect is to, instead of using co-solute particles that are ideal, so they do not interact, instead we can play a bit with all the parameters that we have in solution. So for instance, we can play with the colloid co-solute interaction. We can go from hard repulsion to soft to ultra-soft repulsion, and this changes a lot the effective interaction among colloids. Or, more interesting, we can play with the co-solute properties. So we can exploit, for instance, a co-solute that self-assemble in clusters or linear chains, or that phase separate, or it's close to a second-order critical point. For instance, the most striking example by exploiting this co-solute interaction is the critical CASIMIR effect. This morning we heard about the quantum CASIMIR effect. Here is the analog, but in classical colloidal solutions. You have a solvent that is close to a second-order critical point. So you have, if you're very close to the critical point, you have large critical fluctuations into the solution. You add some colloids in the solution, and the confinement of the fluctuations among the colloid surface give rise to a long-range attraction, which is called the critical CASIMIR force. So then the question, and some results now, it's widely used, this technique to generate colloidal aggregation in colloidal solution, and can be used by just using a critical solvent, like in these cases, but you can also use a critical co-solute. So you can have, for instance, here they have micelles with a critical point. So the question is, can we go beyond and exploit an effect similar to the critical Casimir effect to give rise to long-range forces? So to do that, one could exploit the analogy between critical phenomena and geometric percolation. So in both cases, we have the growth of something. In critical phenomena, we have correlated regions that grows. In percolation, you have clusters that grows. And the control parameter in percolation is the probability to form bonds. And when this reaches the critical value, then you have the spanning cluster, the percolating cluster. Here, instead, the temperature, the control parameter is the temperature. And when it diverges, you have this correlated region that diverge. Both, you already know, because we talk a lot about this, are characterized by scaling and universality. In the geometric percolation, we look at the connectivity length, which is a measure of an average size of the cluster inside the solution. In thermal critical phenomena, instead, you have the thermal correlation length. And both they diverge with a power law that depends, with an exponent that depends on the universality class. So in classical fluids, you have Ising universality class, and in geometric percolation, I will talk about random percolation universality class. Okay, so what do we have to do? So we want to exploit an effect similar to the critical Casimir effect, but with percolation. So what we have to do is basically to calculate the effective interaction between two colloids in a solution with some particles that display a percolation transition. Okay, so how do we calculate the effective interaction? One way to do that is to perform Monte Carlo simulations. In this case, we have hard sphere particles. And what we measure is the probability to find two colloids at a given distance r. You can see a bit that in this movie, the particles are moving. And for each time, we evaluate the histogram of their distances, which is proportional to the radial distribution function of particles. And then you can invert it, and you can find the effective interaction. So quite easy. And then, as I said, we need a COLLOIDAL that it's close to the percolation threshold. So I'm not going to give you details on the COLLOIDAL. I will do it later. But what is important to know is that far from percolation, so when this number, this ratio is far from 1, you will have just monomers. This color scale tells you the size of the clusters appearing in the solution. And then closer to the percolation, you see clusters that grows and gets very large. And so this is what we get. We can have it in our simulations. Okay, so let's measure this effective interaction then between these two hard sphere colloids. But before doing that, we have to stress one important point. And it's the fact that the analogy between critical phenomena and percolation can be exploited, so you have a singularity in the free energy only if the system is characterized by a quench disorder. So what does it mean in our case, in our system, to have quench disorder? It means that the cluster size distribution of our clusters has to be fixed. So we have a chemical sol, basically. These clusters cannot break and reform. So it's something that actually we can do in simulations, because we take our system, we freeze the clusters at some point, and these clusters become basically rigid objects that can rotate and translate inside the simulation box. So that's something that we can do in simulations, of course. And by doing this, we hope to find a long-range effective interaction. The second point is what plays the role of critical fluctuations in this case, since we are exploiting this analogy with critical phenomena, and in the critical Casimir effect, we have density fluctuations which are confined between the surface of the two colloids. In this case, we need something that fluctuates, and the confinement of such fluctuations should give rise to the long-range effective interaction. So in this case, the role of critical fluctuations is given by the size of the clusters. So you can think that in between the two colloids, there are many clusters of different sizes that enter and leave this region between the two colloids. So basically this one. But you can think that the colloids, instead, they see a single cluster whose size fluctuates. So basically it's the fluctuation of the cluster size and the confinement of such fluctuation that should give rise to this, this effect. And indeed, this is the results. So here we have different effective interactions calculated far from percolation up to close to percolation. And as you can see, here we have small repulsive oscillations, but then the interaction potential, this is as a function of the distance between the two colloids, the interaction potential increases and becomes longer range on approaching the percolation point. So what controls the range of the interaction here? Well, in critical Casimir forces, the range of the interaction is controlled by the critical correlation length. And indeed, by a fine-tuning of the temperature, you can go reversibly to short range, to longer range potential in the case of critical Casimir forces. Here, the correlation length is the connectivity length. So the clustering properties of the system should control the range of the interaction. And so what we have done is basically to fit this, this range, extract a decay length, and compared with the connectivity length of the COLLOIDAL, in which the colloids are immersed. And as you see here, they are linearly correlated, meaning that, oops, sorry, meaning that actually it's the connectivity length that controls the range of the interaction. Okay, so another nice thing about this, this effect is that can be theoretically described. And the way we have done this is in the following way. So we have clusters. Clusters have a fractal dimension that is smaller than 3. So these clusters can really interpenetrate, especially small clusters can explore a big region around the large clusters. So it's, if you want to model them as spheres, these are very interpenetrable spheres, which we can consider as ideal, basically. And then we have, this means that we can model the system as colloids, and then we have particles, spherical particles with a radius equal to the radius of gyration of the cluster. And these particles are polydispersed because you have a cluster size distribution, and so also the distribution of these particles is follow this cluster size distribution. So in this way, we can go back to the standard depletion effect for monodispersed particle. In the standard depletion, as I said, you have colloids and polymers outside, which have all the same size. And the fact that these polymers cannot enter in the depletion region give rise to a mismatch in the pressure outside and inside the in between the two colloids. And this forces the two colloidal particles to stay together. The expression of this attraction is a 4-degree polynomial that depends on the size of the colloids, of the size of the depletant particle, and on the density of these particles, and is given by the Asa-Kurosawa expression. So in our case, we can say, okay, we have basically the same picture. Here, these particles are ideal, sorry. And we have basically the same picture, but here, instead of monodispersed particle, we have this polydispersed particle. So we can take, so the polydispersity is known because from percolation, you know the cluster size distribution. So you know how the size is distributed. You know that close to percolation, you have a power law of the size of the particles, which is with an exponential cutoff. So we can take the Asa-Kurosawa potential and weight it with the cluster size distribution. So basically, we have a polydispersed Asa-Kurosawa model. And if you do that and you do your calculation, so you get a curve, and you can check if the curve superimposed with your numerical data. And this is the result. this is not a fit, so there are no fitting parameters. This is basically the solid line, I mean. Basically the results from the theory, and which superimpose nicely with the numerical data. So it means that the effect that we see, this CASIMIR-like effect close to percolation, can be modeled as a depletion interaction with the polydispersed co-solute. Okay, so the things is, of all these stories, that we made a strong assumption, which is our clusters has to be irreversible. So the question is, what happens if instead we let these clusters to break and reform? So we have a physical sol instead of a chemical sol. Do we get the same result? And then the second question is the lifetime of the bonds of this cluster play a role in the effective interactions among colloids? Okay, let's try first of all to look at the physical gel and let's see what happens. So to do that, we have to have some more information on the co-solute that I have used in the simulations. I've used three patchy particles, which are hard sphere particles decorated with attractive sides. They interact, the attraction is given by a square well modulated by an angular function. And this is the gas-liquid phase diagram of this model. So the fact that I've used this model is not really important in the sense that you will get the same results with another kind of model system that follow the random percolation theory. The only important thing is that it has a low density critical point, so I was able to make all the simulation at low density. So a lot of few particles, so was, let's say, fast simulations. So what we have done so far was the following. We were taking points at constant Pagan fraction. So here you have a different cluster size distribution. As you can see, they change. So the cluster size distribution increases on approaching the percolation. So sorry, I didn't say that this is the percolation line. So what we were doing was taking these points and at some point fixing the clusters. But you can do something else also. Instead of moving like this, you can move along a precursor here, along a precursor of the percolation line. And if you do that, we call it a ISO PB line, because the bond probability, PB, is the same along these points. And if you look at the cluster size distribution, it's the same along these points. So if you do the trick of using irreversible clusters, so for instance, let's take this state point and this state point, let's freeze the cluster, let's put two colloids inside and let's measure the effective interaction. What you get is this one, which if scaled by the Pagan fraction, you get the same exact effective interaction. This is because the connectivity length control everything. So if you have the same cluster size distribution into the system, you have the same effective interaction. But if you let the clusters to break and reform, so we go in the reversible case, basically, and you measure the effective interaction, you scale it by their Pagan fraction, you will see that the contact point is the same, but then the range is completely different for all these points. So it means that when the clusters are reversible, the connectivity length is not the correct length scale to account that control the range of the interaction. What is the correct length then? Well, it's intuitive to think that actually is the correlation, the thermal correlation length, and you can prove it if you extract from this effective interaction the range of interaction, as we have done for the irreversible case. You extract the range of interaction and you see how it goes with, for instance, the thermal correlation length extracted from the S of Q. We have done it from the S of Q and also from the radial distribution function. And you see that they have all the same trend. So the range of the effective potential, the thermal correlation length have the same trend. So it means that everything is controlled by the thermal correlation length in the case of the physical gel. Okay, so summarizing irreversible cluster, effective interaction controlled by the connectivity length. Reversible cluster, effective interaction controlled by the thermal correlation length. Then the question is, can we go from one thing to another by increasing the bond lifetime of the cluster? So I make it long-living, unless they are completely irreversible. What happens if we do that? To do that, we have to modify our model of co-solute particles by introducing a barrier H. And we modify also our Monte Carlo metropolis algorithm, because all the time that two co-solute particles form a bond, they have to pay a penalty to enter the barrier. And all the time that two particles want to break a bond, they have to pay a penalty H plus the well depth, epsilon. So by doing that, we can make a system in which all the structural and thermodynamic properties are the same. So you will find the same radial distribution function, the same structure factor, the same energy. But what will be affected very much will be the dynamics. Because if you measure the correlation function of bonds, you will see that on increasing the barrier height, the relaxation will increase, and if you extract the relaxation time, which is this one, the bond lifetime, this will increase of order of magnitude. Most interesting is also the fact that here we go on increasing the barrier, we go to an arrhenius behavior of the relaxation time of the bonds. Okay, so let's take one barrier height. For instance, we take the last value that we have at 0.7. Let's put two colloids in solution and measure the effective interaction. And let's compare it with the case in which there is no barrier. And let's see what happens to the effective interaction if there are differences. So we have done this, and basically you will find exactly the same curve. So the bond lifetime doesn't influence at all the effective interactions among colloids. So, which means that you cannot go continuously from the reversible case to the irreversible case. The reversible case, in which everything is controlled by the geometric properties of the co-solute, it's a singularity, let's say, in our description. Of course, you can think you can recover this the irreversible picture by measuring out of equilibrium, let's say, the effective interaction. So, in this case, here we have sampled the distance between the colloids for very long times which are 100 times larger than the relaxation time of the bonds. But if you sample for smaller times, so I'm comparable with the relaxation time, of course the system will have a memory of the initial cluster size distribution, and so if you see, the green curve is the reversible case, and the dark green curve is the case with a barrier. You will get basically exactly the result. You will recover the irreversible case. Okay, do I have time? No. 5? Really? Okay, just wanted to tell you that actually you can measure experimentally these things. Because, as I said, I used as a co-solute patchy particles, but now it's well known that patchy particles can be done by using DNA nanostars. So you can make 3 patchy particles by using DNA trimers with sticky hands, and for instance, tetramers with this kind of DNA nanostars. And it has been shown that actually they have the same behavior of patchy particles. For instance, one thing about patchy particles is that the valence, which means the number of attractive spots on the particles, shift the gas-liquid coexistence line down to lower densities. And you can do exactly the same with DNA particles. These are experiments. So basically, in principle, they also, it's a recent result, they also shown that they have a percolation threshold, and which is totally reversible. So you have a physical gel, and in principle you can, by using this kind of system, one can try to reproduce our numerical results. So in conclusions, we have proposed different strategies for controlling colloidal interactions by adding additives close to the percolation threshold. The one is by using irreversible clusters, and the other one using a physical, so in one case a chemical sol, in the other case a physical sol. And in the case of the irreversible, the chemical sol, we can get a long-range effective interactions by exploiting a CASIMIR-like effect, which are controlled by the connectivity length. In the case of the physical clusters instead, the relevant length scale is smaller, and it's the thermal correlation length. It's controlled by the thermal correlation length. And the bond lifetime of this cluster do not play any role on the resulting effective interactions, and so the irreversible and the reversible case are two completely separated cases. Thank you.